Very welcome to our Fractal Geometry Seminar, the new location. And my pleasure to welcome Attila Gáspár from University, and he will talk about Lipschitz surjections. Lipschitz maps between self-similar sets.
Welcome everyone. So I'm going to talk about these Lipschitz surjections. So let X and Y be self-similar sets, and we will assume that they satisfy the strong separation condition. So the problem we are interested in is whether there exists surjection from X to Y, which is Lipschitz. We have a result of Balka and Keleti. That if we have X with a Hausdorff dimension strictly greater than the upper box dimension of Y, here Y is a compact metric space. And X is a self-similar set with the strong separation condition. Then there is a Lipschitz surjection. So this means that in the case when X has strictly greater Hausdorff dimension, then we are done. And if X has a strictly smaller Hausdorff dimension, then of course there is no such surjection. So we are interested in the case when they have the same Hausdorff dimension. How can I?
So if you az egér ilyen, tehát az a kis nyilacská, hogyha elnyomsz, és akkor most tudod mozgatni.
All right. So in this case, some partial results are known. So it was shown by Balka and Keleti that if X is homogeneous, then there is a surjection, a Lipschitz surjection, if and only if X and Y are by Lipschitz equivalent. We can consider them as abstract self-similar sets, abstract metric spaces. It doesn't really matter. In fact, we could even assume that they are algebraic spaces, but this is not that important.
So you are looking at them as symbolically, right?
Yes. And
with the restriction that XY satisfies strong separation condition?
Well, we assume that both of them satisfy the strong separation condition. Okay, so there's another result which is quite similar. By Ruan and Xiong. It is quite a recent result. They show that if Y is homogeneous, then we have the same equivalence. So we have these two results where we assume homogeneity on either X or Y, and we have a characterization in this case.
So if Y is homogeneous, then they are by Lipschitz equivalent.
No. I mean that this equivalence holds in this case.
I see. Okay.
So,
hello.
I won't be able to give a complete characterization, unfortunately, but I'd like to give a stronger result that incorporates both of these in some way. So, let's say that we have some positive numbers, R1 and so on, Rn. We say that they are logarithmically commensurable if the ratio of their logarithms is rational for every I and j. In particular, it follows that there exists some R. There exists some R in the interval 0, 1, such that Ri equals R to the Ki, such that Ki is some integer, and also we can assume that the GCD of the Ki's is 1. So assume that we have some X with ratios R1 to Rn, and so we have this R, which we will call Rx, and let Px be the Rx raised to the S power, where S is the Hausdorff dimension of X. So we can see that, so we call this Px the measure root. Of X. The reason for this is that if we look at how the Hausdorff measure scales, when we apply the similarities, the ratios are always integer powers of Px. And so we have defined the measure root. So we have a result by Xi and Xiong which states that so first we assume that x and y have logarithmically commensurable ratios, and then we have the following equivalence, that x and y are by Lipschitz equivalent if and only if, of course, their Hausdorff dimension must be the same, and also so let R and T be the sorry, no, this is not the right notation. So log Rx over log Ry is rational. So this means that the ratios of the two sets are commensurable together. And additionally, we have an algebraic condition that the rings generated by the measure roots must be the same. So if we assume that they have logarithmically commensurable ratios, then we have a complete characterization of by Lipschitz equivalence. But this doesn't say anything about, well, it does say that there exists a Lipschitz surjection, but we are interested in the general case when we assume some kind of logarithmic commensurability condition and we want to give a characterization for Lipschitz surjections. So the main result is that assume that so we assume that x and y are still self-similar sets with the strong separation condition. We assume that they have the same Hausdorff dimension, and we assume that x or y has logarithmically commensurable ratios. Then we have the following equivalence. There exists a Lipschitz surjection from x to y if and only if x and y together have logarithmically commensurable ratios. So the interesting thing in this equivalence is that the right-hand side is symmetric in x and y. So in particular, that means that under this assumption that either of them has logarithmically commensurable ratios, we have, if we have a surjection in one direction, then we also have a surjection in the other direction. Unfortunately, I do not know whether this equivalence holds without assuming this logarithmic commensurability. So let's see an example. So let psi be the inverse of the golden ratio, and take x with ratios psi and psi squared, and you take y with ratios psi cubed times 4, and also psi to the 6th power. So it is, so we can check that their Hausdorff dimension is equal to 1. And it is clear that they have logarithmically commensurable ratios together, since obviously they are all integer powers of psi. So by this theorem, it follows that there exists Lipschitz surjection from x to y, and also from y to x. It is also possible to construct these explicitly, but I won't go into the details. But on the other hand, if we look at this condition of Xi and Xiong, then of course these two are satisfied, but we still need this condition, and it turns out that this algebraic condition doesn't hold, because we have psi cubed, which is equal to square root 5 minus 2. So the ring it generates is just the ring generated by the square root 5, but this is not the same as the ring generated by psi. So in particular, this means that these sets x and y are not Lipschitz equivalent, but there are Lipschitz surjections between them in either way. All right, so I will now talk a bit about the main ideas of the proof. So for that, we will need.
Does this result imply the previous result about homogeneous assumption?
Well, it well, strictly speaking, it doesn't imply it because we also need to prove that if they have logarithmically commensurable ratios, then they are Lipschitz equivalent in that case. But that is the easy part. So yes, this implies the previous result. Originally, my goal was to generalize that result, and I thought that maybe the bias sequence holds also when we have these combinatorial relations, but it turned out that it doesn't hold, but this surprising symmetry in the Lipschitz surjection holds in this case. All right, so we will need the concept of graph-directed fractals. Some of you may not know what these are, so I will quickly write down the definition and the main results. So we have a directed graph and we allow G to have multiple edges between 2 points and also loop edges. And for each edge, we have a similarity SE. It's not really important what the ambient space is. We can say that it is some R, D, or something like that. And we also assume that they are contractions. And then there exists a unique attractor vector consisting of a compact set for each vertex, such that each xi is equal to the union over all vertices j. It can be the same as I, and all edges between so we take all edges from I to j, and we take the union of SE x j. So this is quite similar to the usual iterated function systems. In fact, those are a special case of this when we have a single vertex and several loop edges. So we will need so there is a theorem by Modin and Williams that if G is strongly connected, by that I mean that there is some path from every vertex to every other one. Then the Hausdorff dimension of all these attractors is the same. And also their Hausdorff dimension, their Hausdorff measure is positive and finite. If we do not assume that G is strongly connected, then we have some pathological cases.
Sorry, don't you mean that it's also strongly separated?
Yeah, sorry, I forgot that. So let's say that it satisfies the open set condition. Yeah. So by that I mean the obvious generalization of the open set condition that we have these sets, or we could just take the strong separation condition, which is what we will actually use in this case. All right, so we will assume that G is strongly connected, otherwise we have some pathological cases. So assume that we have a cycle in G, and we can define the cycle ratio as the product over the edges of the cycle, the similarity ratios of the contractions along these edges. And so we will actually see that the previous result that I mentioned holds more generally. So assume that x and y are these graph-directed, which satisfy the strong separation condition. By this I mean that we take one of the sets from the attractor vector, and we do not really care about the other ones here. So we assume that they are of this graph-directed form. They satisfy the strong separation condition, and they have logarithmically commensurable cycle ratios. Then there exists a by Lipschitz. Sorry, I didn't write down that we assume that they are strongly connected. We will always assume that. So there is this Lipschitz surjection if and only if they together have logarithmically commensurable cycle ratios.
So this is every possible cycle in the graph, and you take the cycle ratio for every one of them, including loop edges.
Yes, including loop edges. So of course we have the special case of a usual IFS where every edge is a loop edge. Yes. So clearly we need to assume that. Yeah. And well, we could also assume that they are not cycles but cyclic walls. It doesn't matter in this case, since cyclic wall can be decomposed as the union or multi-set union of cycles without repeating vertices. So we have this generalization, and we will now see why we want to do this generalization to the graph-directed case. So we have the following lemma, which states that if X is graph directed, satisfy the strong separation condition, and so on. The other properties that we assume. And it has logarithmically commensurable cycle ratios. Then X is homogeneous. X is the attractor of a homogeneous graph-directed fractal. By homogeneous, I mean that every contraction on these edges has the same similarity ratio. And also there are some technical properties that we will also need for the proof, but I won't go into the details. So this is the lemma that allows us to reduce the commensurable case to the homogeneous case. I will shortly sketch the proof of this lemma. So assume that so we have some X and we have some graph, and we have the ratios of these edges, but we have a ratio, say R to the X E, where R is a common root of the cycles, but these X E's are, unfortunately, they are not integers, but they are real, positive real numbers. So what we do here is that we take so we take a tree of minimum length paths in this graph. There are some other edges, but we take this tree consisting of minimum length. So instead of R to the XE, I will consider these edges to have length XE, because it's convenient to have an additive setting in this graph. So what we do is we take this tree, and along this tree we can apply some rescaling to each of these sets, for these attractor sets in these vertices. And we can do it, so we can do this rescaling, but then the similarities must be modified. And so their similarity ratio changes. But we can do it in such a way that the similarity ratios on all these edges will be 1. And we can see that the ratios of the cycles do not change when we do this. So in the end, we will have ratio 1, or we could say that these have 0 weight, these edges, and these other edges, which are in some kind of cycle, they will have integer weight, or in other words, their similarity ratio will be integer powers of R. And then we have the problem that we have these edges with similar to ratio 1, which we do not like. For that, what we can do is we can choose, say, this edge, then we delete this edge, and we insert all these additional edges, which are the compositions of this and outcoming edges of that other vertex. I won't go into the details, but if we repeat this procedure, then we will eventually get rid of all the similarities of ratio 1, and then we can just so if we have some r to the k ratio edge, then we can just split it up. By this I mean that we take the endpoint and we add scaled copies along this split edge. And we can check that if we do this procedure, then x will still be the attractor of this modified graph-directed function system, but it will be homogeneous. So this is the main lemma that allows us to apply the results from the homogeneous case. Of course, it is true that the previous results are for the usual IFSCs, but it's not that difficult to generalize them to the homogeneous graph-directed case. So I won't really go into the details of that. So basically, what we do is do this reduction to the homogeneous case, and we prove generalizations of the results of Xi and Xiong, and of Ruan and Xiong, and so we can basically just apply those previous results to this case. But I will also mention another lemma.
Sorry, before you continue, can you just explain what this lemma means in the IFS setting?
So in the IFS setting, basically we have
You just have loop edges, yes.
yes, we have these loop edges, and what happens here is that we insert additional vertices on these edges, so we get a graph-directed homogeneous graph-directed. Yes, so graph-directed homogeneous IFS, and
the claim is the attractor is the same.
yes, well, we have many attractors, but one of them will be this X. And so I will mention another lemma which shows us why we want to do this generalization, since it is, so this thing is, well, we could do this thing without this whole graph-directed machinery. But there's another lemma that X is a homogeneous graph-directed fractal with ratio R. Then X is also homogeneous graph-directed with ratio R to the K. And clearly this lemma has no analog in the usual IFSCs. And the proof of this is quite simple. We just take paths of length, a path consisting of k edges, and we take those as the edges of the new graph. And it is easy to check that the attractors will still be the same. So the reason that we want this lemma is to use another technical lemma of surjections, which says that so assume that we have so first of all, originally this lemma was for the usual or more precisely, it was for the commensurable IFSEs, but it is straightforward to generalize this to the graph directed setting. So this lemma states that assume that x, so we have this, these are the attractors of graph directed IFS, and it is we assume that it is homogeneous with measure root r to the s, where s is the Hausdorff dimension, and we also assume that we have a set omega in the ring generated by P, and omega consists of positive numbers, and it is finite. Then, if we take a set B, which is the union of finitely many copies of these sets, we can take a multiple of each, but we do not do any rescaling. Then, if we have B1 and so on Bm in omega, such that their sum is the Hausdorff measure of B, then that means that so we have these sets, so there exists some k such that if we take the level k sets, we can partition them in some way. Such that this is Hausdorff measure B1, this has B2, and so on. So this is so you can see how the construction. You can see how this is useful for the construction. So say we have this x and we also have the y. We assume that so we take omega to be the Hausdorff measures of the attractors of y, and basically we partition these parts in some way, and this is roughly how we will want to map x to y, and we can do this procedure recursively, and the fact that this k doesn't depend on how these parts are, it will follow that the map that we get is Lipschitz. This is roughly how this goes, and so we have this algebraic condition here, and so the core reason that we need this lemma number 2 is that So we have these two measure roots, but but x and y can have different measure roots, even if they are commensurable together. But if we use this lemma, then we can take the ratios to some power. So if they are commensurable, then we can take such powers that the ratio, this r to the k, will be the same for x and y. And that is how we make sure that if we have this p for x, then it will also be the same for y. And so basically what we do is that we take the ratios, so take the Hausdorff measures of y. By some rescaling, we may assume that they are in the field generated by P. So it is some easy linear algebra, and since P can be shown to be algebraic, and so by rescaling by an integer, they will all be in this ring. And this is how we can apply this lemma of Xi and Xiong. And this is basically how we will construct the surjection.
How will P is algebraic?
Well, it is homogeneous, and we also have this attractor equation. So if we write down the adjacency matrix of G, then we can write down some kind of equation, and it turns out that in the homogeneous case, P will be an eigenvalue of this matrix, or maybe the inverse of P. I'm not sure, but in any case, P is algebraic, and so here we can see how this graph-directed generalization helped us construct the surjection. For the other direction, where we want to prove that they are commensurable together, this graph-directed generalization is not strictly necessary, but it also makes the proof slightly nicer. But it's not essential there. But here for this direction, this generalization is essential. So I don't really have time to go into more details, so I'm going to stop here. Thank you for your attention.
Thank you very much. Questions, comments? Any online people? No, we cannot hear it. But I have a question. So, what if we kick once more into the geometry, now under these homogeneous whatsoever conditions? Is there something known when you assume open set condition only instead of strong separation?
Well, I believe that something may be possible generalizable to that case, but it is probably much more difficult. So recall that we had this result of Xi and Xiong. There is actually a generalization of this result to the open set condition, but that is much more complicated. Here we have this simple thing, this simple algebraic condition, but in the open set case, we also have to consider some ideals in rings and whether these ideals are multiples to each other, and it also relates to the Gauss class number for them, surprisingly. And I believe that some of those results could be probably generalized to this setting, but it would be quite complicated. Actually, they originally had the proof for the open set condition case, but then they made a separate proof for this SSC case because it was so complicated. And it is also true that some sets satisfying the open set condition can be obtained as graph-directed fractals which satisfy the SSC. For example, we have this maybe well-known problem of the 1, 4, 5 and 1, 3, 5 sets. So these are homogeneous similar sets, and the way we can prove that they are bi-Lipschitz equivalent is that we can write this as a graph-directed set which satisfies the strong separation condition, and we can also write this in the same way using the same graph, and that is what shows that they are bi-Lipschitz equivalent. And more generally, so if we have this, so if we have a set satisfying the OSC on a grid, then if it is totally disconnected, then it is true that it is an SSC graph directed. This is also a result of Xi and Xiong.
OSC on the grid means that the translations are integers and it's 1 over L, or the contextual ratio is 1 over integer.
We could just so I just simply mean that we have a square grid and we choose some parts of this. Actually, it is possible to do this more generally on more general lattices like triangle grids and also with rotations and so on. But we also have this special case.
Thank you. More question, comments?
Yeah. So can I take a look at the homogeneous case, the result? Yes. So does this result also hold for the graph directed state? I mean,
no, it is not true that they are bi-Lipschitz equivalent. What we have is that they have commensurable ratios, but this equivalence clearly cannot hold because we had this example. So here we can write them as homogeneous graph-directed fractals, but they are not bi-Lipschitz equivalent. I believe that there is no characterization known for the bi-Lipschitz equivalence in the graph-directed case. But under some additional assumptions, Xi and Xiong also have results for the graph-directed bi-Lipschitz equivalence case.
What question, comments? So, if not, then let's think.